Hello and all, welcome to the Math Magic Show. In this one, we're going to take a look at finding the limit as x approaches 0 of x plus 1 over 1 plus sine of x raised to the 1 over x squared. I have the limit as x approaches 0 of x plus 1 over 1 plus sine of x, and the quantity is raised to the 1 over x squared. First, let's see, is there a problem with this limit? In other words, can I just plug x equals 0 in and see what happens? Well, let's see. I'm going to have 0 plus 1 over 1 plus sine of 0, so replacing x with 0, and then 1 over 0 squared. So I replace x with 0 everywhere. Look at the consequences. Now it's going to look like 1 over 1 plus 0 because sine of 0 is 0. Then raised to the 1 over 0 because 0 squared is 0. And then this is going to look like basically 1 raised to the 1 over 0, roughly speaking, which in other words would be like 1 raised to infinity. So there's something happening here. So because we have 1 to infinity, that kind of form, somewhere we're going to have to apply a L'Hopital along the way. Let's take a look. So first I'm going to write this as limit as x approaches 0 of e to the ln of x plus 1 over 1 plus sine of x raised to the 1 over x squared. And again, the reason for that is that the e and the ln functions are inverses, so I can write it that way. I'm not changing anything, I'm just making it look different so I can take the limit more easily. It's a common trick. Okay, then after that I'm going to bring that 1 over x squared out, so it's going to be e to the 1 over x squared outside, and then ln of x plus 1 over 1 sine of x, and that is by the basic power rule of logarithms. Place that in front of the logarithm there in the exponent. So next I'm going to do this. Limit as x approaches 0 of e to the 1 over x squared. And it's going to be 1 over x plus 1 minus ln of 1 plus sine of x. And I'm doing that because x plus 1 over there, 1 plus sine of x in the previous step. You can convert that to a subtraction by a basic property of logarithms. So it looks as shown here. This is going to be equivalent to the limit as x approaches 0 of ln x plus 1 minus ln of 1 plus sine of x over x squared. I can put that under the whole thing there by a basic property of fractions, as I'm sure you know. So now look what happens. I'm going to have e and replace. So it's going to be 0 plus 1 minus ln of 1 plus sine of 0 over 0 squared. So I'm pretending that I can replace x with 0 at that step. And look, it's going to give me now e to the ln of 1 minus ln of 1 over 0, because 0 squared is 0, and then sine of 0 is 0, and 1 plus 0 is 1. That's why in the second logarithm here it says ln of 1 in this position. But now finish this up. ln of 1 is 0. Alright, so it's going to be 0 minus 0 over 0, which is e to the 0 over 0. So this is proving that we have a 0 over 0 kind of form in the exponent. It tells us L'Hopital is applicable here, okay? So let's take a look. I'm going to have the following. The limit as x approaches 0 of e, and then differentiate the top. So the derivative of ln of x plus 1 minus ln of 1 plus sine of x. And in the bottom, I will have the derivative of x squared. Remember, when you apply L'Hopital, you differentiate the top individually, you differentiate the bottom individually. It is not the quotient rule. Okay, after that, I'm going to have the following. X approaches 0 differentiates. So that's going to be 1 over x plus 1 minus 1 over 1 plus sine x, multiplying the derivative of the inside, which would be the derivative of 1 plus sine of x. And the derivative of x squared on the bottom is 2x by the basic power rule. So these are the derivatives formed. Notice that I'm color matching here so you can see how the pieces are fitting together from here. Okay, and I'm not spending too much time going over the actual process of finding the derivatives, because at this point I just want to get through the limit. Hopefully you've seen most of these derivatives and you know how to find them. So next I'm going to have limit as x approaches 0 of e to the x plus 1 minus 1 over 1 plus sine of x times the cosine of x. And that is so because the derivative of 1 plus sine of x from the previous step is cosine x at this step. And I left little blanks there because now what happens is the following. If I did try to actually plug in x equals 0 into this step, into the last step that you see there, I would again end up with some kind of undefined form, like 0 over 0. Okay? I'm not going to show that check, but it would work out that way. So what is that telling me? That means I got to differentiate again. So in other words, I got to find the derivative of 1 over x plus 1, and then the derivative of that quantity there with the sine and cosine. And then same thing with the bottom. I got to differentiate the 2x again. So I'm using essentially L'Hopital twice. Alright, let's carry that out. So for the first one, I'm going to be the limit as x approaches 0 of e to the negative 1 over x plus 1 squared minus that other derivative, which would be negative 1 over 1 plus sine x. Now the derivative that you see in red, I'm not going to show you the detail. Here, every single little step, if I wanted to show the derivative of, 1 over 1 plus sine x, cosine x, it's a whole separate sequence of like 5, 6, 7 steps. So that's why I'm skipping that, okay? So I have the following now. In the bottom, the derivative of 2x is just 2. Now look at this. Why is this helpful? Because now take a look. It's going to be e to the negative 1, replacing x with 0 gives 0 plus 1 squared. And then for the second one, it's 1 over 1 plus sine of 0. And then in the bottom is a constant 2, so that stays. So that step, I'm just replacing x directly with 0. Now it's going to give me e to the negative 1 plus 1 over 2. Okay, so at this step here, the negative 1 there in black is present because in blue up here, it's negative 1. So look, 0 plus 1 is 1. 1 squared is 1. Negative 1 divided by 1 is negative 1. For the other one, it's 1 over 1 plus sine of 0. Well, sine of 0 is 0. It goes away. So this is 1 over 1, which is 1. And in the bottom, I have my 2. So I'm going to have e to the 0 over 2. Okay, because negative 1 plus 1 is 0. That's going to give me e to the 0, which is lessly equal to 1. And that is the value of the limit found somewhat carefully. I did skip some of the steps involved in finding some of the derivatives just to save time and make this reasonable. But that is it. Thank you so much for watching. Please leave a like and subscribe, and I'll see you in another video.